Good afternoon. My name is Hannah Slater, and I am a junior in the Randall Research Scholars Program, majoring in chemical engineering and chemistry. This semester, I worked on a project titled Machine Learning for Prediction of Non-Routine Events in Cancer Patients under Dr. Zhang and Dr. France at Vanderbilt University, continuing the same project I worked on this past summer. Cancer is essentially when normal, healthy cells go haywire and essentially don't do what they're supposed to be doing. And so because these cells can be anywhere in the body and there's a multitude of things that can go wrong with them, there's many different modalities of treatment for these cells for cancer. And so seen here are some of the different modalities. And so a single patient in a single day could go to radiation, surgery, and more targeted therapies. And so these are things like immunology and things that target the more specific cancer, while that other patients at the same time could be going to surgery, radiation, and chemo. And what ends up happening is there's a giant mess of patients going to see different doctors and different clinicians. And what this really is doctor or clinician-centered care rather than patient-centered care, which we would like to think it is. And so this is a problem. In addition to this, if a patient, say, goes to see a doctor at urgent care or at the emergency room closer to their house instead of their primary care physician, their doctor at the, say in this case, Vanderbilt Medical Center does not know about this visit unless the patient explicitly tells them. And so because of this, there's many different issues. And so ideally, all patients have an optimal care path. And so ideally, all patients would remain on this theoretical optimal care path, but we all know that that doesn't happen. And this is due to non-routine events, abbreviated here as NRE, and this leads to a clinical deviation in care. And so it's really hard to get patients back on this optimal care path because of some of the issues I outlined earlier. And an important thing to note is cancer patients are increasingly being treated in an outpatient setting. So this idea that it's really hard for them to go see their doctor is really important. And so the goal of our project is to collect passive and active surveillance data on patients, both when they're in and outside of the hospital, and feed this into a predictive model so that we can alert their clinical team and eventually push them back onto this optimal care path. My work over the summer worked on the processing of a lot of the passive surveillance data. This included Fitbit watches and data from smartphones using Google Timeline, but my role this semester focused more on development of algorithms for this predictive model. And so machine learning essentially is the use of computers to find patterns in data that otherwise would take us a really long time to find these patterns. And so one important thing to note is that in healthcare, these projects have been exclusive to clinical data. So this is the data when the patient is only in the hospital. So we're missing all that data when the patient is outside of the hospital. And this is very important, like I said, because patients, especially for cancer, being treated more in this outpatient setting where they are not spending all of their time in the hospital. And so with this, we hope to learn the likelihood of a non-routine event for these patients so that we can predict them before they actually have them. And we would also like to gain some intuition on what some of the factors are that lead to this conclusion through the different models. So essentially how machine learning works is we take all the data we've gathered on the patients and split it into a training set and a test set. And from there, we run the training set through a hypothesis function, which gives us a prediction. Now, with this, we calculate how the function compared to what we actually wanted it to output. And so this is an example of a loss function of something that's a binary classifier. So this is something like true or false or yes or no, or in our case, non-routine event or no non-routine event. And so we compare what it gave us versus what we would like it to give us. And we optimize this by updating the different parameters theta that are in this function. And from there, when we've officially optimized the function and the different parameters, we get a model. And from there, we can use the test set data and run the test set data through the model and see how well it performs and evaluate the model. And from there, we might make more models or change the model and start the entire process entirely. And so some examples of different functions that can be used for this, I'm going to talk about now. One of these being logistic regression. And so as you can see, at high values of x, the model predicts a value closer to 1, whereas at lower values of x, it is closer to 0. And so this is what I was talking about earlier, this idea of a binary classifier. So either they have, in this case, if we want to predict spam email, whether or not email was spam or not. In our case, we like to predict a non-routine event versus no non-routine event. Yes, and another example of a algorithm for this is a gradient boosting tree, and essentially what this is it's a decision tree. So you work your way from the top of the tree down the tree, and at each like branch of the tree, you essentially ask it a different question. So there's different weights assigned to each of these things, and it gives you a value. So you slowly grow this tree so that more branches are added slowly. And so an example of this in the real world would be, say, if a hospital wanted to determine whether or not an insurance claim will be rejected. So the things at the top of the tree are more important in classifying this rather than the things at the bottom. And as you can see, based on the answers, you get yes or no's as to whether or not the claim will be rejected. In our case, we would expect to see something more like this. An important thing to note also is these gradient boosting trees are very useful in giving us more of this intuition of what we want from the data. So like I said earlier, we want to know more about like what factors are playing a role into developing these algorithms and what factors are at play. So knowing things like these that are at play so that doctors in the future can recognize these are really important. And so another example of something I'm developing is neural networks, which essentially we take all the data that we've collected on these patients and feed it into these pink nodes. And so at each of these nodes, a computation is performed, and they get fed through these green hidden networks. And so essentially what these are doing is they're, like I said, performing a computation at these different nodes, but these help show different nonlinearities in the data because, as you can see, they all intersect and overlap. And this gives us one output, like I said, this binary classifier. And one of the problems with these kinds of algorithms is they're kind of a black box. We just know that we put something in, we get something out. We don't really have as much intuition as to why they're working. And so an example of a real world example of this is if, say, we wanted to predict whether or not these pictures were dogs or not. So we'd feed it a bunch of pictures of dogs. And ideally, we'd be able to have a model that predicts that this is, in fact, a dog. In our case, we would like to be able to predict that if this patient is going to have a non-routine event or not. And so in conclusion, we are working towards collecting all of this data on the patient in and outside of the hospital. And so we have an existing data schema, and using this, we can develop algorithms for this predictive model. And we have future directions in testing these algorithms against patient data in the hopes of alerting their clinical team and pushing patients back onto their optimal care path. And like I said, this semester I focused on developing these algorithms for the predictive model. And so with that, I'd like to take any questions.
So what kind of data is collected on the patients, and how does this impact their day-to-day life?
So we plan on collecting data, both passive and active surveillance data. And so this whole idea of surveillance is there's little to no minimum input of the patients themselves. And so we're trying to minimize how much the patients themselves interact with the data. And so with that, all the patient has to do is go about their day-to-day life and wear a smartphone or carry a smartphone with them and wear a Fitbit. And so this is going to be tracking both their macro location with the smartphone, being able to tell us where in the world that they are, and their micro activity of what are they doing at these different places using the Fitbit watches. And so this is some of the data that we're collecting through the Fitbits. And so as you can see here, there's lots of data, and this is actually one of the things I worked on over the summer, is processing all this data so it's actually in a usable format, because prior to that it was not. And as far as the geolocation data, using Google Timeline, which is what we're using, we only get latitudes and longitudes, and as you can probably glean, they're not very important. So one of the ideas of my project this summer was to build geofences of patient-reported locations, and these are self-reported locations that are important to these patients, so say their home or their church or somewhere that's important to them. And so building these geofences and only tracking when they're in and out and getting all of the data like that seen here of when they're in and out of each of these places. So overall, and this is in addition to collecting clinical data from, yes, when they are in the hospital, in addition to surveys that they are filling out on a weekly basis, and anytime they do have a non-routine event, so that we do know about that, so we can hopefully predict them again in the future.
Who will be able to see the results of the algorithms?
So that's one of the good questions, and one that we keep asking as we're developing these algorithms is, so there's this idea of explainable machine learning, and so we don't know how much of the models will necessarily be able to say as a factor, because we know the different weights. We don't know necessarily if that's enough that a patient should necessarily see, or if we can necessarily say, oh, well, you did this yesterday, and so that means that you're going to have a non-routine event tomorrow. And so we don't know if we want to necessarily scare the patients or not. So as of now, we're planning on it only being their clinical team, and from there, them deciding how to move forward.